word about the Institute. It was founded in 2012 by a generous grant from the Simons Foundation. And it's the venue where we get people together, mostly in areas of theoretical computer science, for a sustained collaboration over an entire semester. So we want people to come here as long-term visitors and talk to each other and maybe generate new perspectives, often combining different angles of approaching the same problem area. So we create programs. We expect the public, the community of theoretical computer scientists to be applying to host programs here. So we would look forward to your applications in the future. And that's how we choose which programs we will have here, depending on great applications. While we are the venue that actually gathers together the top theoretical computer scientists and young talent every semester, we also like to look at the rest of computer science, the rest of the topics that have impact in society, other fields like physics and biology and so on, from the lens of theoretical computer science. And I think that it's a very productive lens to look at all these topics from. Now, specifically returning to AI, AI and theory have been more or less the same thing for a little while in the history. A long time ago, we used to think of AI and theory as part of the same sort of sub area of computer science. They come together, they diverge, they come together, and so on. Even machine learning has very tight connections to theory in the past, but maybe in the world of pack learning and so on. And now there's a renewed connection again. And I think at this moment where AI is having this enormous impact on society, where there's a bit of trepidation and a bit of excitement about AI around in society, it's a very public topic now. The natural native pessimism that theoretical computer science brings to anything, any field of inquiry, might be a good partner for the can-do attitude that AI industry has. So I think that there's a need for a renewed connection, a strong connection between theory and AI. And I hope this workshop and the entire program we have this year on large language models, and we've had programs on federated learning coming up, and we have a program on modern paradigms and generalization. So we're doing a lot trying to relate AI, machine learning, LLMs to theory here. And I think some of these seeds of collaborations are already happening, and we hope this workshop will encourage others. And I want to thank the organizers, Sanjit and others, for putting together this great sounding program. One small housekeeping rule: we do not allow any food or drink in the auditorium except for bottles of water. So please bear that in mind when you enjoy the workshop. We'll have all our food outside. Yeah, thanks. Thank you, Sampath, and welcome to you all here in the room and online to this Simons Institute workshop on Trustworthy AI, theoretical aspects of Trustworthy AI. My name is Sanjit Seshia. I'm a professor of ECS at UC Berkeley, and I'm one of 5 organizers who have put together this particular workshop with the assistance of many people here in the room. All right, so we have a 5-day program, an exciting 5-day program for you all. The goal of my talk this morning is just to give an introduction to the topic area of this workshop, as well as to give a description of some of the results that I think are emblematic of some of the progress that the community has made towards the goal of Trustworthy AI. And so that's really the goal for this talk today. And then we'll have another series of talks, stage setting, tutorial style talks that will cover the rest of the day today. All right, so I want to start, of course, with the very beginning question, which is, what do we mean by trustworthy AI? And I'd like to position this in the larger question of what does trustworthy systems mean? I think there are different views on exactly what that term means, depending on what person and what communities you talk to. And so I'd like to give a little bit of a union of what various people have written about this in the literature. So I'll start with an article by Jeanette Wing, which appeared in Communications of ACM, where Jeanette Wing, someone who has worked for a long time in the general area of trustworthy systems, talked about the typical attributes that people
used to define what trustworthiness means of systems in general, computer systems in general. And so in this article, she talks about properties like reliability. Does the system do the right thing, or is it correct? Safety, also related attributes of liveness, then security, privacy, availability, usability. These are all typical properties that people talk about for systems in general. But really the focus of our article is also about what are the new attributes, new properties, new classes of properties that you have to talk about when we are focusing particularly on AI and machine learning systems. And so to that end, she introduces a bunch of other properties. Of course, one that is, of course, the bedrock of all machine learning evaluation is evaluating the accuracy of machine learning or AI models. In some sense, the attribute of the model to be able to generalize beyond the data that was trained and tested on. Robustness, which is understanding how sensitive the output of the model is to small changes in the input. Fairness, talking about whether the outcome is biased in any way. Accountability, transparency. So do we understand if an external observer is looking at a machine learning based decision-making system, would they think that, would they have a clear understanding of the reasoning process underlying how that decision was arrived at? And then interpretability or explainability, which is being able to, related to transparency, being able to understand how the model works. And this is particularly important in this age of deep learning and large language models, where we're dealing with black box models that we don't necessarily have full access to. All right, so there's a whole bunch of different properties here coming from this paper by Gina Ping that characterize this notion of trustworthiness. It's really like a union of many different desirable properties of AI systems. But that, like I said, that's one article, and there are others in the literature. And I won't be in this. My goal is not to survey everything, but just to give you a few representative examples. So a related term that we've all come across, I'm sure, is AI safety, right? So AI safety is this term that is used very commonly in the AI community and the community involving users of AI. And again, this is often used in multiple ways, but one way is relating to this question that we want to ensure, how do we ensure that AI systems don't act in ways that are harmful or dangerous to society, right? And so that's, of course, it's not a formal definition, but this is AI safety, I think, is a term that is being used pretty informally to describe a whole area. But depending on who you talk to, the notion of AI safety can take on different meanings. So safety in this term is not necessarily the same as how safety is used in the article by Gina Ping. It could be much broader than that. It just means that, oh, I think of an AI system as being safe if it satisfies its specification, what I intend it to be. There's also this question and this term of alignment, which is a little bit more squishy, right? So an AI system is said to be aligned if it does what people want it to do that is consistent with their values or societal values. So there are all of these terms around AI safety, and for that reason, it is a term that's used for a whole area, but we're not going to spend too much time talking about that particular or trying to define that. Instead, I want to introduce two related notions. So one that I and some co-authors introduced nearly 10 years ago in an article is the phrase verified AI. And in that paper, we introduced verified AI as the goal of designing AI systems that have strong, ideally provable assurances of correctness with respect to mathematically specified requirements. Now, this definition is rooted in the community I come from, which is formal methods, where what we'd like to do is be able to first mathematically formalize the requirements for any system that we'd like to design or analyze, and then try to prove or disprove that the systems meet that we're looking at meets those requirements. Now, in some cases, the task of being able to prove that a system meets requirements is undecidable. And this is why, I say ideally provable, but we know that in many cases, we're not going to be able to, give a decision procedure to solve that problem. And so we have to compromise in one direction or the other. And then the other thing that we wanted to emphasize was the design process, that we can have a lot of great theory around this goal of trustworthy AI or verified AI. But what we'd really like to do is embed that theory into tools that people will actually use in the design process. So I'll touch upon this again when I get a little further in this presentation. And of course, there's been multiple communities within computer science and engineering looking at this problem of trustworthy AI. And so some of us actually got together last year and tried to unify the various different approaches from AI alignment and probabilistic approaches, empirical approaches. And so that led to this paper that is talking about this goal of guaranteed safe AI. And here, this is a bit of multiple communities coming together and trying to unify their approaches and definitions. But the essence of this guaranteed safe AI notion is that we want to give a formalized quantitative safety guarantee that is produced by analyzing three things. So of course, you have the AI system, but you also have a world model. And in this context, the term world model refers to a model of the world around us that is producing the data that the model is trained on, right? So we want to be able to capture those assumptions, essentially write a specification of the world that is producing the data. And additionally, we want to write specifications, and then we want to produce a verification, a verifier that will take the world model, take the specification, take the AI system, and be able to give some kind of a safety guarantee or disprove that the safety properties hold. Okay. All right. So much for definitions. So now I want to give a little bit of a perspective on what the challenges are and what's been done so far. So this picture over here is the standard picture of formal verification that, if you have any introductory class in formal verification, people will describe what a verifier is using this diagram. Okay, and so what is a formal verifier? It takes in three inputs: the system under verification, a model of the environment in which it operates, which is the world model, and the specification that it must satisfy phi. And the question that the verifier asks is, if I execute S in the context of E, so I compose S and E together, that's what that means, does it satisfy the specification? And like I said before, this is a Boolean question, so it has a yes/no answer. Either it does satisfy it or it does not satisfy it. Okay, question?
From the environment if you're going to put them together anyways afterwards?
Yeah, so the question is, why separate the system from the environment? It doesn't have to be that way, but the reason is typically the system is the artifact that you are analyzing, right? And so that's the focus of the verification task. The environment is essentially all the assumptions that you're making about the world in which the system is operating. So the environment is more of a model, whereas the system is the artifact, right? Ultimately, you're going to compose both into a common model, but I think conceptually it makes sense to separate them out.
Yeah, if you're talking about things like robustness, then the environment can even be adversarial.
Indeed, yeah. So
you don't have control of it. It might be adversarial if you're thinking of robustness and things like watermarking and so on.
So you can fix the system, but you cannot fix the
it's almost like a game.
Yeah. So I don't know if the people online would have caught that, but Somesh mentioned that in the context of robustness and adversarial analysis, the environment is your threat model. It's your model of the adversaries, right? And so that is not part of the system. Okay. So like I said, about 10 years ago, we tried to think about what is different about this particular problem in the context of AI systems. What we identified there, were a few different things, which is in the Communications of ACM paper down here, but I want to emphasize some unique challenges that AI systems, at least for formal methods people, introduce. And I call this the inputs problem. Okay, so what do I mean by that? Usually for conventional hardware and software, coming up with the SE and phi is not a hard problem. I mean, it's challenging, but it's not the biggest problem that one has. But for AI systems, this can be incredibly hard. And so in particular, if you look at something like autonomous vehicles, and think about modeling the world in which the autonomous vehicle is operating, we have a number of challenges that arise. First of all, these are open worlds, meaning that we don't even know what's in the world necessarily have good models of how they behave. The interfaces to the world are complex. You have these sensors, LiDAR, array of cameras, GPS data, other kinds of telemetry data. So it's really high dimensional sensor interfaces. And then, of course, many of these AI systems interact with people. And so you have to have some way of modeling that interaction and the behavior of people. So that imposes an additional layer of complexity over conventional hardware and software. So that's just 3 aspects for the world model. But then if you look at other things like the specification, there are certain things that are unique that go beyond what formal methods typically deals with. So for instance, as we all know, a lot of the successes of AI have been in perceptual tasks, like dealing with computer vision tasks or natural language processing, natural language generation, all of these things. And these are tasks for which it's hard to formalize what exactly the task is in mathematics. And yet, for formal methods, we'd like to start with mathematically specified requirements, right? So there is a big gap there that there are certain tasks that you can't really write a formal specification for. Additionally, machine learning or learning systems, by definition, many of them interact with their world and then they evolve over time. And so they also interact with people, and what people want can also change over time. So the specifications themselves are not static, they change. And then finally, the way in which properties are specified in the AI world, in the machine learning world, tend to be based on providing data sets and label data and things like that, rather than logic or automata-based formal specifications that we're used to in the formal methods world. So there is a impedance gap there, okay? And so that's another layer of complexity in coming up with the specification. And then the final layer of complexity has to do with the systems themselves. I think the size of the AI models has been growing, if you look at some of the plots, exponentially over the last decade in terms of the number of parameters. These are very large. They are black box, as I alluded to earlier. And also, you need to, in order to specify and verify these systems, many times you have to look at them in the context of the larger system in which they operate. For instance, for autonomous vehicles, it's not enough to just analyze the behavior of a deep neural network that does different object detection or prediction tasks. You need to essentially analyze the safety of the entire vehicle operating in its environment. And that, of course, creates a much larger system to analyze. Anyway, so these are some of a selection of the challenges that we identified in this paper. And it's an example of how this problem is different from other problems that the formal methods and the control theory and cyber-physical systems and programming languages community has handled with for developing other trustworthy systems. Okay, so yeah, Somesh.
I take a little bit of a cynical view of this. So I think it is, for good or bad, a lot of the action in this space is in industry. Right? Yes, everybody will agree with that. Right? So I think I think it is the pace of products that is happening, and it's like, you come up with a very nice theory, you have a paper, workshop, and so on. Well, while those companies are now going to after the next product. So I wonder whether the hurdles are technical, or is it that, you have to somehow penetrate the business cycle there.
Yeah.
And I think that is, the bigger problem. I don't think it is.
Yeah. So great question, and actually a great segue to my next slide. Okay. So Somesh's point was the challenges may not be just technical; they're also what should we call that? they're really socio-technical, right? Because it also deals with industries forging ahead, and then the rest of us the theorists are trying to catch up, right? So I'd say two things. Number one, I don't think that's unique to AI systems, right? So if you're working in hardware verification in the 1990s, I remember, people like Randy Bryant would say that verification is always at least a decade behind where the processor design is. So I feel like we're always in that mode. But secondly, I think it also motivates this workshop, and so let me just explain what I mean by that. So here on this slide, I have admittedly maybe a random way of classifying trustworthy AI research into they don't look like three axes, but three different categories. There's theoretical work, then there's work on tools that we either work with people who design AI systems to apply it to improve the trustworthiness, or give it to the designers themselves. And then there is the work on designing AI systems for different applications. And in my opinion, I think, like Somesh was saying earlier, there's been a lot of work in industry on building AI systems, industrial scale AI systems. And I think there has also been work on building tools to analyze those systems. Admittedly, many of them are very applied, right? What we are missing is the connections to theory. So that's what I'm trying to indicate here by the width of these arrows. There's a lot of work on building AI systems and then trying to analyze them or use tools to uncover bugs and flaws and then maybe iterate that process. And I'll give you two examples in the next 15, 20 minutes. But what we need to do is really strengthen these arrows, right? We need to imbue more of the theory into the tools so that we can give guarantees about when we can verify something and when we can't, and how long it'll take and all of that. And we also need to push the theory more into the system design so that we can get more trustworthy by construction AI systems, okay? So that's really the motivation for this workshop. When we wrote the proposal, we wanted to actually build these stronger connections between theory and all the other areas that are trying to work on trustworthy AI. All right. So, so as I mentioned a little earlier, some of us actually coming from different communities, from the core AI ML community, from the formal methods community, from programming languages and control theory, a number of us came together to write this position paper on guaranteed safe AI. And one of the things in this paper that I actually like is the section at the end that we put together on somewhat concrete challenge problems, right? So I want to actually mention two of these challenge problems and then present some progress from the applied side that the community has made towards that. So the first challenge problem area in this paper is autonomous vehicle safety. The idea here is similar to what I talked about just a few minutes ago. If you have an AI-enabled autonomous driving system, doesn't have to be fully self-driving, could be partially self-driving. You want to be able to analyze its safety in the context of certain driving scenarios. And the question is, how do we do that? How do we build the algorithms and the tools to be able to analyze this? And in particular, even if we just focus on one type of AI system, which is the use of deep learning for perception. Okay, so that's problem number one. Problem number two is AI for coding, right? So as we all know, and this is an area where industry is just forging ahead, generative AI, large language models are already being widely used in industry for generating code. But if the guarantees, if anything, at best are being given by testing. And so what we really like to do is make sure that we can give stronger guarantees. And this is an area where actually there are decades of research on software verification that we can leverage. So, so that was another challenge problem. In particular, we made it a little bit more specific. We talked about the challenge of translating code from one language to another. The advantage of this particular version of the AI for coding problem is that the specification is a little bit more constrained because you start with a source program, you want to generate a target program, and you want some notion of equivalence between those, right? So that's problem number two. So what I'd like to do in the next 15 minutes or less is to give you some examples of results on both of these. Yeah.
Problem 4.2, right?
Yes.
Do you also need a proof that your system satisfies
Yeah.
the form specification? And what's the form of a proof
Yes,
there?
correct. Good. So ideally, yes, one would like to have a proof. I think, as we both know, the problem is incredibly hard. So I mean, just from using hybrid systems theory, right? It's undecidable to do reachability analysis, and so we know we can't prove this in general. And I think today the best approaches are statistical in nature. That is, doing what is called statistical model checking or statistical verification. Okay, great. So let me talk a little bit about autonomous vehicles. I'll talk a little bit about code transpiration, and then I'll conclude. Okay. So both of these are areas that I and my collaborators have worked on quite a bit. So what I'll speak about in terms of results will be from our own work. So in the context of autonomous vehicles, one of the big tasks that we have to do is modeling the world in which these autonomous vehicles operate. And our particular approach was to develop a new programming language, a probabilistic programming language called Scenic, to be able to model the world in which an autonomous vehicle works. And so here is a little Scenic program that models a scenario of a badly parked car that pulls into a path of the approaching, this is the foreground ego vehicle as it approaches. And so I'm not going to go into the details, but Scenic, since it's a probabilistic programming language, every variable in the Scenic program is a random variable with an associated distribution. Some distributions are explicitly provided, and some are implicit in the library. And what you were seeing down there is Scenic used to generate data or simulations. So when you run Scenic and you connect it to a backend simulator, in this case, the Carla autonomous driving simulator, every time the program runs, it generates a new configuration sampled from the distribution. We try to do a diverse sampling, but all of these simulations have the same characteristic, that it's the badly parked car pulling into the path of the ego vehicle. So Scenic was actually designed 7 years ago, and it's already widely used in industry and academia. So here's actually a video from a case study we did with the American Automobile Association and LG a few years ago, where we are trying to use Scenic to define scenarios and test them in the AV testing facility that AAA has here in the Bay Area. And what you're seeing here is a particular scenario where the autonomous vehicle is coming up on the turn, and there's a pedestrian dummy that's crossing, which will stop and hesitate a little bit in the beginning of the road. And we saw this scenario in simulation where it seemed to recognize that there's a pedestrian and yet would drive into it. And so when we replicated this on the real road, we expected maybe it's not going to show up because there's a gap between simulation and reality, but in fact it did, right? And so finding these sorts of edge cases, I think, it's still a big challenge for the industry, but a lot of progress has been made with the help of tools like Scenic. So I want to show you another case study that we did with Boeing, just to show you how these tools today, the practical tools that exist for autonomous vehicle safety, can already be used in the overall design flow of these kinds of systems. Okay, and so this particular case study that we did with Boeing was for autonomous airplane taxiing. And so this was an experimental aircraft taxiing system developed by an R&D group at Boeing. And this was a neural network called TaxiNet. So TaxiNet would take in images from a camera that was mounted on the right wing of an experimental aircraft. And you see an example of what that would look like on the right here. And so that image would then be fed into a neural network. And the job of the neural network was to estimate what is called the cross-track error, which is the deviation of the nose of the plane from the center line of the runway. And then that estimate would go into a conventional controller that would control the steering and throttle. And the specification of this particular system is that the plane's nose must be within 1.5 meters of the center line, left or right. So it shouldn't deviate laterally more than 1.5 meters. All right, so here's an example of TaxiNet operating. This is in the context of a simulator called X-Plane that was used by Boeing in this particular case. And you see it's doing a pretty good job of keeping the plane on the center line in spite of all of these skid marks that are obscuring them. Okay, so that's what it should do. All right, so now what we did with our tools, Scenic is the tool to model the world in which TaxiNet is operating, and Verify is, I haven't talked about it, but it's an open source system with a backend suite of verification algorithms. And so what we did here was we modeled runway scenarios in Scenic after talking to Boeing, specified the safety property in temporal logic, then ran the verification algorithms to falsify the system, meaning that we were trying to find violations of the safety property. And then once we found those violations, then we had additional algorithms to be able to debug and try to understand why failures occurred and what the causes were. And then once we understood those, we could then use that to generate new data and retrain the neural network. Okay, and then there was a final step also, which is runtime assurance, which is recognizing that the scenario that's modeled in Scenic may not be actually what is true at the time when the system is in operation. And so you want the system to be self-aware and recognize that it's going to enter an environment that it doesn't have safety guarantees for. So that's the runtime assurance piece, which I won't talk about today. All right, so very quickly, I'm going to go through this. So here's the model in Scenic. Without looking at the code, basically what Boeing told us is up here in the top right. They told us that what can change is the time of day when the system is in operation, whether there's clouds in the sky, what kind of clouds there are, whether there's rain, how much rain there is, and the position and orientation of the plane on the runway. And so once we had that model, we can specify the safety property, which was a temporal logic assertion, which basically said that sometime in the first 10 seconds, the CTE value falls below 1.5, and then it stays there henceforth. And so we ran our falsification algorithm, and it found about 4,000 automatically generated simulations, of which 45% of those violated this property, and 9% actually violated in a pretty bad way. That is, it just drove off the runway. And so here's an example of one of the simulations. So it's early morning, low light, light rain. And you can see the center line is sort of drifting off to the right there. So it's proceeding to drive the plane off the runway entirely. Okay. And so now we could use tools to analyze what went wrong. And originally we thought it's probably these things like skid marks on the runway. But to our relative surprise, we found that the biggest correlation between the failures was with respect to time of day. And so what you're seeing here is a representation of the safety of the system with respect to this, what is known as the robust satisfaction function. So basically what it means is that negative is unsafe and positive is safe. And you see that TaxiNet is unsafe in the early morning hours, similar reasons to what you saw in the video. And then it behaves safely for a bit in late morning, early afternoon, and then it falls again below zero in the mid-afternoon hours, and then again in the evening. The mid-afternoon was a bit of a puzzle for us until we used Scenic to generate data corresponding to those times, and we found that there were these shadowing effects of the plane's wings on the runway when the sun was above, and that was throwing off the neural network, right? So this is a case where we're using formal methods to be able to identify biases in the training data. And then once we understand that, we can do what is called counterexample guided retraining, which is essentially use these counterexamples to safety to generate new data and retrain the neural network. And when we do that, we find that we can get much better performance. So here again, same environment conditions. The top is the original neural network. The bottom is the retrained one after counterexample guided retraining. You can see at the top, it's just driving off the runway. And at the bottom, it's doing a pretty good job of staying in the center line.
Hardware verification, for instance, software verification?
Yeah, it is. I think, so the question is, are the techniques different from what is used in hardware verification or software verification? I would say at a high level, there are similarities. So in hardware verification, actually the workhorse of hardware verification in industry is called assertion-based verification, which is essentially running simulations and trying to violate temporal properties. And in that sense, it is similar, but the algorithms under the hood are quite different. Yeah, Bettina?
A couple of details how you do the counterexample guided retraining?
Maybe I'll do that offline, just in the interest of time. But yeah, happy to talk about the details later. And just to summarize this, for the retrained model, you get the blue curve, which is consistently above 0. So it behaves safely. All right. Okay. So just a few minutes on code transpilation. So again, that was deep learning, and one can say, well, deep learning is now the old AI already, because everything is large language models now. So what can we do for large language models, right? Can we apply verification there? And so this is, of course, a much more challenging problem. But the good news is we have been able to, in certain limited settings, get strong formally verified guarantees, even with LLMs. And so this is a relatively recent result. So this is work that is joint with my colleague, Alvin Chung, here at Berkeley, done by our student, Sahil Bhatia. And this is in the context of code translation. So the context for this is that you start with code in some source language. Imagine you have legacy code in C or C++, and we want to be able to translate it to a target language, which, for example, in the context of machine learning kernels, it might be in some domain-specific language, in some DSL that is well targeted to the new machine learning accelerators hardware that many companies are creating. And so you'd like to be able to do this translation, but you want the source program to be equivalent to the target, right? So this is a problem that Alvin has been working on for a decade, and he has been using classic program synthesis methods. In particular, there is a method called counterexample guided inductive synthesis based on the use of symbolic methods like SAT and SMT solvers that is quite widespread. And so in this paper in 2023, we had a system called MetaLift that would go from, in principle, any source language to any target language for programs that are purely functional. But the dirty secret behind MetaLift was that, like in many program synthesis tools, you have to build in a bunch of heuristics for the synthesis algorithm to search the grammar that specifies the space of possible programs efficiently. And that was a lot of manual work. And so what is CGIS? CGIS is the technique behind this is essentially you can think of it from from a view that is closer to machine learning as something that is similar to query-based learning, where you have a learner interacting with one or more oracles that can answer queries, right? In the context of CGIS, there are two types of queries you use. We call them positive witness, which is positive example queries, which is simply saying, give me input-output examples for a program behavior. And the second type of query is a verification query, where you get a counterexample back if the property is not satisfied. Okay, and so Sushmit Jha and I, several years ago, did some theoretical work where we generalized what the general idea behind CGIS into a broader framework that we call Oracle-guided synthesis. So the idea in Oracle-guided synthesis is you formalize the interface between the learner and the oracles as a set of query and response pairs. But the synthesis algorithm is something where you design both sides of this interface. So it's basically the idea is you agree on a protocol that you're going to use for synthesis, which is your O, and then you design both sides of that protocol. So the synthesis algorithm is really the pair of the learner and the oracle. And in this paper, we show, similar to the results in query-based learning about sample complexity or query complexity and what can be learned and not learned, we show in the context of program synthesis similar results of what counterexample guided synthesis can learn and not learn. Okay. And like I said, there are connections here to topics in machine learning, but also in complexity theory. Like I know this idea of prover verifier games has recently gained popularity in the context of LLMs. And these are actually concepts that are very similar to Oracle-guided synthesis. And so as a goal of this workshop, we have a whole day where we would like to explore these connections more closely. Yeah.
As an oracles, did you look at many oracles at the same time?
Yes, you can have multiple oracles. And I can talk more about this later, but like I said, Wednesday is going to be mostly thematically on this particular topic. Coming back to the problem that I talked about of lifting, the reason I did this segue to Oracle-guided synthesis is because that's the viewpoint that we took to now using LLMs for verified code synthesis. And so, so last year, Sahil built this tool called LLM Lift, which is presented at NeurIPS, where the idea was we're going to start similar to counterexample guided synthesis. We can, one mode of interaction is using input-output examples of behavior. But additionally, what we'll do is we'll also add oracles, add LLMs as additional oracles that can be queried. And the idea there is you can think of two types of queries made to the LLM. One is, we'll call it the LLM program prompt, which is basically asking the LLM to giving it the source program along with some examples and asking it to generate the target code that is equivalent to the source, right? So generate a program P such that P is equivalent to the source. The LLM comes back and gives you some P star. And then once the LLM gives you P star, we go back and say, now help me prove the correctness of this code. So we go back to the LLM and do what we call an LLM invariant prompt, which is ask the LLM to generate invariants, auxiliary invariants, loop invariants, even possibly preconditions and things like that, to help us prove that its previous response is in fact correct. Okay, and then the LLM comes back with a candidate invariant, and then we query our formal verifier saying, here's what the LLM gave us, program P star along with the invariance I star. Can you prove the correctness of this particular code? Right? And so the idea here is to enlist the LLM in the verification process by having it generate these proof artifacts that otherwise the program verifier would have to do, and which end up being actually some of the hardest pieces of the verification problem. All right, and so long story short, LLM Lift did way better than we expected. So what I'm showing here is a selection of the results where these are various code translation tasks going from Java to Spark, C to a DSL for network packet processing, and then C to two different DSLs for machine learning. And this is the previous state of the art, the symbolic tools, which have, as I mentioned, a lot of built-in heuristics. And this last column is what LLMs, incorporating LLMs can do, and we can basically solve most, if not all of the benchmarks, right? So I'm presenting both of these examples in the spirit that there's actually been quite a bit of progress in terms of practical tools to be able to make AI more trustworthy, or the AI systems more trustworthy. But we need more connections with theory. So that's really one of the goals of having this workshop, that we want to be able to learn from each other and build more connections. All right, so with that, here are some of the communities that we have sought to draw participants from, but it is not exhaustive by any means, right? And we really, like I said, I think a goal of this workshop is to try to learn each other's language and learn from each other and try to build more collaborations across areas. All right, so here's the plan for the rest of the workshop. So today, Monday, is essentially the introductory day. So we have 3 tutorial-style stage-setting talks covering different key topics in trustworthy AI, but from different perspectives. Okay, so Bin Yu will be giving the talk this morning for an hour and a half, and then Stuart Russell will talk in the afternoon, and then after that, Somesh Jha. Okay, so we have a great program today, and I hope all of you will stay and participate in this program. And then after that, we have talks by all of the different participants coming from the different areas. And like I said, we've tried to assign themes to every day, although it's not perfect because of having to juggle people's travel schedules. But broadly speaking, Tuesday, the theme is safe learning with respect to some notion of formal specifications, right? Maybe it's like a control theoretic specification, or it's like a more traditional program specification. But that's sort of the theme is how do you incorporate that safety specification into the learning process. Wednesday, the theme is machine teaching and program synthesis, so being able to draw connections between what's being done in the program synthesis world and what's being done in the query-based learning machine teaching world. Thursday's theme is reinforcement learning, trying to make reinforcement learning more trustworthy. And then Friday's theme is interpretable and explainable AI. Okay, so those are the set of things that we have. Like I said, I think this workshop is just the beginning. So there's probably fodder here for an entire Simon's program. And hopefully, we'll be able to start to make the connections there towards not just a Simons program, but also more meetings between the communities. So I want to mention very quickly was one such meeting. So some of us have come together to create a new conference on neurosymbolic systems, which is really trying to build these communities together. And the first edition is in a month's time in Philadelphia. But we like to have more of these sort of meeting places for the communities. Okay, with that, let me switch over because we're already a little over time. So I'll switch over to Bin Yu's talk, and I'm happy to take more questions in the break.